Let's bring all this together as far as probability and hypotheses. So we've talked about the various statistical techniques we've covered. We've talked about hypotheses. Now let's talk about the importance of statistical significance in testing the hypotheses. So again, an inferential statistic is used to infer the results on a sample to a population by comparing the obtained test statistic to a population's test statistic probability distribution and compare that to the critical test statistic. So that's what we're actually doing. And the process of obtaining a test statistic from the mathematical equations and comparing that to a critical test statistic on the probability distribution is to get statistical significance. And again, what we're looking at is whether or not we accept the results and we present them. In other words, is it statistically significant? And again, I really almost wish that it wasn't, the term statistical significance tends to be a little confusing to some people because it is just a measure of probability. I almost wish it was called statistical probability, the probability that we are correct in our inference, that what we found in the sample we would find in other samples, in other words, in the population. So within this framework of hypotheses, both alternative and null, we basically have type 1 and type 2 errors that can occur. A type 1 error is an error in hypothesis testing in which the null hypothesis is rejected when it's true. In other words, putting this into simple English, it's when we claim there's an effect when in reality there wasn't one. And as a science, as a culture, if you will, we've decided this is the one we're most worried about. We're worried about making the type 1 error. We're worried about basically saying we're rejecting the null hypothesis. In other words, we're accepting the alternative hypothesis. We're claiming an effect when in reality it isn't there. The type 2 error is one that we probably make a lot more often. It's an error in hypothesis testing in which a failure to reject the null hypothesis when it's false. In other words, we basically say we didn't find anything. It's not statistically significant. But the reality is actually it was. So again, we don't know, at least from a single study, whether we're making a type 1 or type 2 error. This is more hypothetical. This is kind of the framework we use to conceptualize how we're testing hypotheses. And what we get is a decision matrix. So at the top in the brown column, we have reality. So for example, the null hypothesis is true, the alternative is false. In reality, there is no programmer effect. There is no difference. Our theory is wrong. Or the null hypothesis is false and the alternative is true. There is a program effect. There is a difference. There is a gain. Our theory is correct. So that's the reality. Now, we can't actually know the reality from a single study. We can start to infer it as we do more and more studies, as we look across multiple researches. But at the same time, what we do know is what we conclude. So within a particular study, a particular sample, we decide based on the statistics whether we're going to accept the null hypothesis, rejecting our alternative, or whether we're going to reject the null and accept the alternative. So in other words, we're going to say there was no real effect, or we're going to say there was an effect. Now, if we say there was no effect, and in reality there was, that's a type 2 error. The odds of saying there is no effect or gain when in fact there is one. The number of times out of 100 when there's an effect, we'll say there is none. So basically, remember that our p-value, we're setting that at 0.05. So we're only accepting 5% of the possible outcomes for us to claim an effect. That doesn't mean that there's a 95% chance when we fail that we're wrong. There is such a thing as a very high probability there's no effect, or even situations where our test statistic is 0. There is literally no pattern or effect there to be found. But when we get closer, we have to start realizing we're probably making a type 2 error. We don't know, but it's one of the reasons that sometimes research has to be careful. And it's also been a problem with a lot of research that when studies fail to find statistical significance, they tend to end up in the trash can. They tend not to get published. They tend not to get reported, which means that there are times when we may be making multiple type 2 errors and never realizing it because none of it's ever getting published. The type 1 error, though, is we say there is an effect, and in reality there wasn't. This is the type 1 error, the odds of saying there is an effect or gain when there in fact is none. And this is where we've set our alpha at 0.05. That's our bar, or our level of confidence. We have to be 95% sure or better before we claim an effect. Now, the two other possibilities do have names as well. So, for example, we have the type 1 and type 2 error. What happens when we reject the null hypothesis? We say there's no effect, and we were right. That's confidence. The odds of saying there is no effect when in fact there is none. So basically, this is where we start getting into a little bit about rigor, how rigorous a study is. And finally, there's power. The odds of saying there is an effect or gain when in fact there is one. So basically, we often talk about making a rigorous but powerful study. And one of the ways we increase power is whether it's a non-directional, two-tailed test, or a directional, one-tailed test. We're more likely to find an effect. In other words, we have more power if it actually is true when we get in this box. So our goal is to be either in the confidence or power box, and what we're worried about is being in one of the error boxes. Now again, individually and in one particular study, all we can do is basically calculate the probability that we have power, the probability we have confidence, the probability that there's a type 2 error, or the probability there's a type 1 error. It's generally multiple studies that start to create a pattern that lets us know. For example, if we're looking at depression and anxiety and we have hundreds of studies that have found an effect, that means we're much more confident that there is power there, that we are actually finding what we mean we're finding. There is a relationship and it is there in reality. Likewise, if we actually did a study on anxiety and depression and found that we weren't quite statistically significant, we'd probably say there's a pretty good chance we're making a type 2 error here. There was something about our study or our particular sample that resulted in this not actually occurring. However, if multiple studies have continuously found there's no effect, we're pretty confident that we can say there really isn't an effect here. So again, just kind of walking through this very quickly, there's four possibilities. The confidence level, that's where there wasn't an effect and we claim there wasn't an effect. Then we have the type 1 error, the odds of saying there is an effect when in fact there isn't. We say there's an effect, but the reality was there wasn't. This is the type 1 error, and this is what we're worried about. We don't want to be in this box. It's one of the reasons we calculate a p-value. The type 2 error is probably happening more often, but we're okay with having more error in this category because of the nature of science. That generally speaking, other people are going to research this as well, and if there's a meaningful effect there in reality, it probably will eventually be found. And finally, what we're hoping to end up in is power. There was an effect, and we found it. So again, there's kind of a back and forth. You can't, if you increase the chance of a type 1 error, you decrease the chance of a type 2. If you increase the chance of a type 2 error, you decrease the chance of a type 1. And basically, we've acknowledged that as we decrease the chance of a type 1 error, we're increasing the chance of that type 2 error. And likewise, there is not necessarily a similar relationship as far as confidence level and power, as both of them are correct. They're the boxes we hope to end up in. But again, we're simply measuring the probability of where we are within a single study. If we look at the actual two outcomes that can happen if we actually reject the null hypothesis and claim there's an effect, again, we can either be right or we can be wrong. And we want that chance of being wrong to be 5% or less. So if you try to increase power, you also increase the chance of ending up at the bottom row, and you also increase the chance of a type 1 error. So we can ratchet up the power to guarantee we find something. So for example, if I thought that there was a very small effect or an effect that would be hard to find, there's a lot of things I can do to increase the chance that I might find it. And I might find a statistically significant effect. However, would other people find that with less powerful studies? So I've probably increased the chance of being in the type 1 error box, even though I have a very powerful study. Likewise, when we look at the type 2 error, if you try to increase your confidence, you'll increase the chance of winding up in the top arrow. In other words, the more confident we are that there isn't an effect, we may also be missing the fact that there's an effect. And this, again, is up to the researcher to balance, to communicate, and it's one of the reasons reading through the method sections of what was done gives us a lot of the information in a study to answer these questions. What were they doing? Were they finding an effect in a way that basically convinces you that it was actually more focused on confidence, which means that they're probably much more likely to be correct when they say there's an effect? Or were they really ramping up the power to find an effect, which makes you also start to wonder, would you find this in other studies? So just bringing this down to a much simpler state of affairs, we have the state of affairs versus statistical decision, whether we support the null hypothesis or whether we reject it. and again, whether that's true or not. If we reject it and that's what we say and it's true, we're at no error in power. If the null hypothesis is true and we don't reject it, we basically say it is true, we have no error or the type 2 error. So again, just kind of thinking about this is another way to conceptualize what we're trying to achieve with our hypotheses when we actually bring it to the hard math of statistics. So some of the things to think about is you do want to be as powerful as you can be within reason. One of the ways that you can increase power, almost all of our inferential tests are more likely to find differences the larger our sample size. And this is based on the idea that the bigger your sample, the more representational it probably is of the actual population. We can also think of effect size, big differences between the levels of our IV, focus participants' attention on that IV, and use a reliable DV. So for example, if we are measuring personality, a reliable DV might be a well-established personality measure that takes 10 minutes to actually perform, which would be more likely to find differences as it's a better tool, it's a better, more defined instrument than, say, a simple 5-minute, 5-item measure of personality. If our differences in our IV, so again, we might think of, for example, an alcohol. If I'm looking for the effects of alcohol on your mood, I might be looking at a small difference, might be the difference between 2 drinks and 3 drinks. A bigger difference might be the difference between no drinks and 10 drinks. Also, if the IV is an intervention, we want to make sure that focus the participants. So for example, let's say the independent variable is the addition of study time. We want to make sure people are engaging in that study time, that people are making advantage of this ability. In other words, if we simply are presenting a slideshow on studying and no one's paying attention to it, have we really manipulated the IV at all? So all of these are things that we can think about methodologically about making a study more powerful. So again, being as powerful as you can be, at the end of the day, it's not just a matter of do we find a statistically significant difference. We also want to think about the effect size. How meaningful is that difference? Did we use an appropriately sensitive DV, for example? So we might ask, do people like chocolate? Yes, no. That's a 2-option answer. Or we may ask them, how much do you like chocolate? Not at all to a lot on a 7-point scale. We're more likely to find variability, sensitivity, with that second question. And that's another thing we can think about as far as effect sizes. It's harder to find differences in simple measures, especially dichotomous measures, yes and no, for example, versus measures that are more mathematically spread out or continuous. So the main points, again, coming out of all of this is the level of statistical significance indicates the probability that results occur by chance. It's a marker of confidence. It's a probability. Statistical significance is necessary, but not sufficient for research to be successful. We also want to look at the effect size and the broader significance of results, also important. So for example, if I told you about a study where I found that a new study technique that cost $10,000 per student resulted in a change of their overall test scores of 5 points, is 5 points worth $10,000? However, if I told you that an intervention has been found that costs very little money, let's say just an hour of time, we'll call that $20, results in a change in test scores of 10 points on a 100-point scale. Those are 2 examples of thinking about the broader significance and also the importance of the study. We want to increase the chance of achieving statistical significance by using a powerful research design, but we also want to realize that the more powerful the design, the possibly harder it's going to be to infer that to a larger population. In other words, we want a powerful research design, but we also want to make sure that it's in the realm of normal behavior. So for example, if we're looking at the effects of alcohol and driving, if no one is drinking to the point of near unconsciousness in driving, then there wouldn't be necessarily a good point to running a study that looks at the effects of someone at that level. We'd probably want to find out what is the average level of alcohol consumption where people are choosing to drive, and that would be a more meaningful study to look at, even though it might not be quite as powerful. So the big points coming up from all of this as we move into the next test is 1, our p-value needs to be equal or less than 0.05, which represents a 5% chance or smaller of actually making a type 2 error or type 1 error. The type 1 error is claiming an effect incorrectly, so that's what we're worried about. We're worried about making the type 1 error. we're worried about claiming an effect when it actually isn't there. We found one in the sample, but it wouldn't be there in the population. Once we have statistical significance, we also need to consider the nature of the relationship and how big the relationship is, the effect size. And effect size isn't just mathematical, it's also practical. Is this a meaningful increase that people should be concerned about and be willing to implement in their own lives? Causation is not just done by the type of technique or statistic we use, it's done by methodology. There has to be a statistical relationship found that is significant. We also need methodologically to assert temporal precedence. In other words, we need control of that IV. And our study itself needs to rule out any other possible confounds that could explain the effects that we found. And a true experiment has absolute manipulation of the IV, usually through the process of random assignment, controlling any possible other confounds.